Hi everybody, my name is Limane Badre. I am PhD student at University of Galma in Mechanical Engineering Department. Today I would like to present my research on the influence of the encapsulant material on the thermomechanical deformation within solar cells under operating conditions. First, I'm going to tell you why you need to know this influence. Photovoltaics is the direct conversion of the solar radiation into electricity using semiconductors material that exhibit the photovoltaic effect. A standard PV module consisting of the many layers as shown in figure number 1. The main purpose of this composite structure is to provide a protection from external environment and mechanical damage, and also provides the electrical insulation. Okay, now I'm going to define the failure of the PV module. The failure of the PV module means it decreases in its electrical energy over time. The failure of the PV module can be due to a number of the causes. The figure 2 see the first cause of the failure is the corrosion and around 45%, and the second is the breakage of the cells. The second cause is related to variation of the thermal stress caused by daily temperature variation. Problematic of this research. The PV industry is dominated with ethylene vinyl acetate as encapsulate, mostly due to it is low cost. Other polymers such as the polydimethylxylene and thermoplastic polyurethylene have gained interest and are being tested for better encapsulation of PV modules. The main objective of this work is a comparison of the mentioned encapsulate and selecting the optimum one based on its thermomechanical effect on the solar cell and the operating condition. Finite element modeling. The finite element method is a numerical technique used to solve complex mechanical, physical, and mathematical problems. There are a wide range of the software packages available, such as Abacus, ANSYS, COMSOL, Multiphysics, and more. Each software requires the input the geometric model, material properties, and boundary condition. In this work, we use the Abacus software. Now I'm going to define the inputs of the finite element model. Geometric model. The reference module in this work, consisting of the 60 solar cells not interconnected, will explode the symmetry of the geometry by modeling a quartet to reduce computational effort and time. Loads and boundary condition. The finite element model is subjected to one daily temperature range of the Ouargla city, Algeria. The selected day out of the January as shown in figure number 6. Material modeling. The choice of the material appropriate model is key to determining the current magnitude of the thermomechanical effect of the PV module. In this research, we use the linear viscoelastic model for the encapsulate material EVA, PDMS, and TPU, and linear elastic model used for remaining material. Table 1 gives the summary of the all material properties used in this simulation. Validation of the material model. To validate our material model, we use the experimental result obtained by Enter et al., or use the digital image correlation technique to measure the gap displacement between two adjacent cells. The PV module placed in climatic chamber and then heated to 90 degrees Celsius and then cooled to minus 35 degrees Celsius. The figure 7 shows the temperature profile to which the laminate is subjected. The cell gap displacement was calculated and compared with experimental results, as shown in figure number 8. The good agreement can be tested. Result and discussion. The stress in the solar cell are evaluated after one thermal cycle. The shrinking of the external rails of the PV module glass and backsheet at minimum cycle temperature. This leads to compress of the solar cells. So the compressive stress is predominating in the solar cells at lowest temperature. We use the minimum third principal stress to evaluate the compression stress within the solar cell for each type. Figure 9 shows the compressive stress for each encapsulant type, EVI, TPU, and PDMS. We can see that the compressive stresses decreases from minus 63 megapascal for EVA to minus 14 megapascal for PDMS. Figure 10 gives the variation of the first principal strain within solar cells over time. As it can be seen, PDMS provides the least strain change during the day and thus provides the maximum time of the crack initiation. On the other hand, the strain height change in EVA is the most providing it the minimum life. Conclusion. Within the present work, the finite element analysis was to study the impact of the encapsulated material on the thermal stresses developed under operating conditions. We used the three different materials in this research: EVA and TPU and PDMS. It can be concluded that you use the encapsulated material with the lowest deformation range ensures a longer lifetime of the PV module. Maximum life of the PV module is provided when the PDMS is used as an encapsulant. Thank you for your attention.